Okay, so good morning to all. Sorry for the inconvenience. There is some issue here in the college for the power supply. So now, again, we will recall that what we learned in the last lecture, because it's already have a so actually we learned about the synchronous impedance method in last lecture, okay, which is the method to find the voltage regulation. Okay, so again, there is the number of methods to find the voltage regulation, like a synchronous impedance method. Now today we have to learn about the ampere turn method or the MMF method. The third method is the zero power factor method, and it is also known as the Pottier method. Okay, and I think these methods you already learn in your laboratory sessions, because most of the time I think the synchronous impedance and the ampere turn or MMF method you are perform the experiment, maybe. Okay. So in last lecture, we learned about the synchronous impedance method. So it is a very easiest method to find the voltage regulation. Okay, to find the voltage regulation, what we have to do in synchronous impedance method, we have to find three things. One is the open circuit characteristic, second one is the short circuit characteristic, and third we have to find the armature resistance, which is known as the RA. Okay, so to find the armature resistance, what we have to do, we are giving the DC supply to the armature of the alternator, and by taking the ratio of voltage and current, we can find the value of resistance. But we are measuring the DC resistance. So what is the value of AC resistance? It is the 1.5 times of the DC resistance. So suppose if you are getting the value of 10 ohm, then you have to multiply 1.5. So actually, your armature resistance is 15 ohm. Then we have to give the open circuit test. In open circuit test, we are not connecting any load with the alternator, and we are increasing the field current. Okay, the field current is more important. Without field, no EMF is generated. You are aware about that now maybe. So when you are increasing the field current, your voltage, which is generated in the alternator, it is again increase. Okay. So we are increasing the voltage up to my rated voltage or terminal voltage of the alternator. Then the second test we are doing short circuit test. So let me show you the here it is not shown. So in short circuit test, what we are doing, we are short circuiting the two terminals. Okay, if we are short circuiting the two terminals, then it's also okay. But instead of that, we are short circuiting all the three terminals, and we are increasing again the field current. Okay, as you increase the field current, your short circuit current is also increased. Well, how much amount of field current we are increasing? Up to the rated armature current. Suppose you have a nameplate. In nameplate, they are giving you the rated terminal voltage, and they are also giving you the rated current. So we are giving the or increase the field current up to the rated current. So now we have OCC, we have SCC. So in single graph, we are plotting the open circuit characteristic also and short circuit characteristic also. Now assume at the field current 2 ampere. So at 2 ampere, we are measuring short circuit current also, and at the same field current, we are measuring open circuit voltage also. Now we are taking the ratio of this voltage and this current, that is known as my synchronous impedance. From that, I can find the synchronous reactance because I already have the value of armature resistance. So now I have ZS, XS, and RA, all the three I have. And then I can plot the phasor diagram, or you can say the vector diagram. From the phasor diagram, I can get the value of E0. Terminal voltage we already I have. And then we can take we can find the voltage regulation by having a no load voltage minus full load voltage divided by terminal voltage multiplied with 100. So that is my synchronous impedance method. Now second one is known as the MMF method, or it is known as the ampere turn method. Okay, so today we have to learn about the MMF or the ampere turn method. So again, MMF method is also used to find the voltage regulation of the alternator, and it is also known as the ampere turn method, or it is the Rother's MMF method because it is found by the Rother's. Okay, so it is also known as the ampere turn method. Why it is known as the ampere turn method? Anyone having any idea why MMF method is known as the ampere turn method? Let me give me the answer. What is the unit of MMF? Suppose EMF, what we are measuring EMF, we are measuring the EMF in terms of voltage. Okay, so there is a MMF also. EMF means electromotive force. Same way, MMF is the magnetomotive force. So what is the unit of MMF? Or the equation of MMF? Can anyone having the idea what is the equation of MMF? Those who are attending the session online, are you getting my voice clear? Or there is a echo? See, all these things you already learned. What is the equation of MMF? Yes, it's Ni. In which MMF is equal to Ni, in which N is the turn, which turn, number of turn in the alternator. And I is the current flowing, sorry, not alternator, my mistake. N is the number of turn of the field winding, and I is the current flowing through the field winding. So the unit of the MMF is ampere turn. Okay, as we are measuring the EMF in terms of voltage, we are measuring the MMF in terms of AT. If you remember, it is ampere turn. So that's why this method is known as the ampere turn. Ampere turn is nothing but it is the unit of MMF. And the equation of MMF is N into I, when N is the number of turn of the field winding and I is the current flowing through the field winding. Okay, now it's clear. So now again, you are performing this in laboratory or it is pending MMF method? Yaad nahi hai. See, you must have to now because see in GTU the term end is 30 September. Only 25 days or 23 days remaining. Okay, and now in this semester either in GTU or MU, no mass progression is there. Remember that thing. You must appear the final exam. Now, if you are not reading anything, you are failed. Okay. So, again in MMF method, we are performing the same test, which is known as the ACC and SCC. Open circuit test and short circuit test, we have to perform only. Okay. But now instead of finding the synchronous impedance, we are finding the MMF. So, let's say how we can find. Okay. So this MMF method is based on the result of again open circuit and short circuit test that we already have learned in the last method, which is synchronous impedance method. So you can see here it is already written. MMF is required, which is a product of field current and the turns of the field winding. Why we require the MMF? Because MMF will generate the flux. Without flux, no voltage is created. You are aware about that. If you do not have a magnetic field, you are only rotating your alternator or armature, no voltage is generated. When voltage is generated, when your conductor cut your magnetic flux, then and then EMF is produced, Faraday's law of electromagnetic induction. So to generate the field, magnetic field, or to generate the magnetic flux, we require the MMF, which is magnetomotive force. You can see here why we required MMF. Here it gives the two purpose. One is it must have an MMF to necessary to induce the rated terminal voltage on the open circuit test. Okay, and it must have an MMF equal and opposite to that of armature reaction of the MMF. Okay, we have armature reaction also. So when it is the armature reaction, MMF is generated. Okay. In armature reaction, MMF is also generated. So our main MMF, we must require to oppose that armature reaction MMF. Okay. Now you can see here, the key points. So in the most of the cases, as the number of turns of the field winding is not known, suppose you have an alternator. I'm giving you the alternator. You are not the you are not in the company which is manufacturing the alternator. Okay, you are the purchaser. Suppose I required one alternator, so I am asking the rating. Suppose if you require the alternator, what you are asking for? Okay, yes, look. Suppose if you want to purchase one alternator, which rating you are giving to the supplier? Suppose I want to purchase one induction motor. So I'm going to the shop, I'm asking that give me 1 HP motor, which having a single phase supply. Now, if you want to purchase alternator and you are going to the shop, what you are asking for? Rating, which rating? HP? HP is the rating of the motor. For alternator, which rating we require? Yes, you can say the voltage you require, then single phase or 3 phase we require. Then what is the rating? Yes. We already solved too many examples. In that example, I am giving you the data. So in that data, what I am giving you the data of alternator. Suppose you have a transformer. What is the rating of transformer in terms of? Okay, we have T. Let me. What rating they are giving here? They are giving the voltage frequency which connected it is given. Here it is the open circuit test and short circuit test. Otherwise, let me show you what data they are giving here. Okay, so you must have to give the kVA rating. Either you require a 1000 kVA or a 1000 MVA, which type of. So the rating of the alternator as well as the transformer is in terms of kVA or MVA. Okay, it is not in terms of watt. Suppose if you are going to purchase any load something. So if you are taking the fan, it is 60 watt. If you are taking the light, if you take any light when you are going to the market, or if you want to purchase a LED, or if you want to purchase a CFL, what you are asking? Give me 40 watt light, give me 16 watt LED, give me 20 watt LED. So that's the rating. But in a generation purpose, the transformer and the alternator having the rating in terms of kVA and MVA. Okay. So when you have a nameplate of a transformer, then or you have a nameplate of the alternator, they are never indicating the how many numbers of turns you have in a field winding or how many turns you have in your armature winding. Okay, so that's only here says in a key point. In most of the cases, the numbers of turns of the field winding is not known. If you are a manufacturer, then you are aware about that. But if you are a purchaser, then you are not aware about that how many numbers of turns are there in a field winding. In nameplate also, they are never said about that. What they are giving in a nameplate, kVA rating, voltage, current, frequency, star connected or delta connected. That type of details they are giving in the nameplate. So what we are doing, we are calculating the MMF in terms of current only. Okay. So the field MMF which is required to inducing the rated terminal voltage, on open circuit test, result and the open circuit characteristic, this is denoted by FO. Now remember this thing that we required, FO. What is FO? What is FO? FO is the field MMF which we required for open circuit test. Okay, FO is the field MMF which we required for the open circuit test. Now, as you are aware about the synchronous impedance, it is consists of two components. Let me show you. Okay, this is my ZS. It is consists of two components, which one is XS, another one is RA. XS is my synchronous reactance and RA is my armature resistance. So it is written here. Synchronous impedance ZS is consist of two components. Okay, armature resistance, another one is synchronous reactance. Now again my synchronous reactance XS is again divided in two components, which is, okay, I already give you that in PPT. You can see here. Again my XS is divided in two components. What is that? XL and XAR. What is XL? It is my armature leakage reactance, and what is XAR? It is my armature reaction. Okay, reactance of armature reaction. So again it is written here. So synchronous reactance, again it is divided in two components. One is armature reacted reactance XL and the armature reactance, armature reaction reactance, which is XAR. Okay. So in the short circuit test, the field MMF is required. Okay, in open circuit test, field MMF is required to generate FO or open circuit voltage. Again, in short circuit test, we require the field EMMF. Why? To overcome drop across the armature resistance, which is RA, and the leakage reactance, and also to overcome the effect of armature reactance. So in short circuit test, we require the MMF to overcome the drop of the armature resistance, to overcome the drop across the leakage reactance, and to overcome the effect of the armature reaction. Okay. But the drop across the armature resistance and this leakage reactance is very small compared to this armature reaction. So that's why we are neglecting this drop. Okay. So here I am giving you the whole theory in detail, but when you have to write down, you have to write down in a points. Okay. Otherwise, this theory will be of 4 pages. So you have to write down in your own language. Okay. So in a short circuit test, we are calculating, or field MMF circulates the full load current only to balancing the armature reaction effect. Only to balancing the armature reaction effect. We are neglecting the drop of armature resistance, and we are also neglecting the drop of leakage reactance. Why? Because compared to armature reaction, it is very small. So we are neglecting it. Okay. So now in short circuit test, we have the field MMF, which is divided by FAR. So we have two terminology right now. One is FO and another one is FAR. FO is the field MMF for open circuit test. FAR is the again field MMF, but in a short circuit test. Okay. So now under the short circuit condition, as resistance and this leakage reactance has no significant role, so that's why we already neglect that. The armature reactance is dominating, that I already told you, and hence the power factor is purely reactive circuit, is zero lagging. Hence FAR gives demagnetizing ampere turn. Okay. Now see, in short circuit test, what we are doing, we are not considering two things. Which one? One is armature resistance, and second one is leakage reactance. So in short circuit test, the main part is my armature reaction. Main part is my armature reaction. Okay. So again, we have to go for the armature reaction. In armature reaction, we are learn about three things. Which three things? These three things. Either my load is purely unity, either my load is zero lagging, or either my load is zero leading. Okay, so any load I have, suppose your load is purely resistive, so your power factor is unity. Suppose your load is purely inductive, then your power factor is lagging. Suppose your load is purely capacitive, then your power factor is leading. Here also we have same case. Okay, but generally what we are doing, most of the time my load is inductive in nature. So as my load is inductive in nature, so my power factor is lagging. Okay, you can take any case, always they are giving you power factor lagging because 90% of our load is purely inductive. Okay, we do not have a load of purely resistive and capacitive. We have the load of a combination of RL. So it is inductive in nature. So that's why my armature reaction effect is demagnetizing in nature. Suppose if you are aware about the question paper, in GTU we are asking about that. What is the effect of armature reaction when I have purely capacitive load? In purely capacitive load, my effect is magnetizing effect. And in purely inductive load, my answer is demagnetizing effect. In NU paper, we have both the question. What is the effect of armature reaction when you have only capacitive load? And what is the effect of armature reaction when you have only inductive load? So in inductive load, we have demagnetizing effect. My actual flux, my armature flux oppose the main flux. So overall flux will be reduced. As overall flux will be reduced, it is demagnetizing. In capacitive effect, my actual flux and my armature flux both is in same direction. So total flux increase, so it is known as the magnetizing effect. Okay. Now you can see here. This is the short circuit test and this is the open circuit test. Okay, we are give the two terms. One is FO. FO is the field MMF for the open circuit test, and FAR is the field MMF for the short circuit test. So you can see here the two components total field MMF, which are FO and FAR. So FO is for open circuit characteristic and FAR is for the short circuit characteristic. You can see here. Okay. Now, if the alternator is supplying full load, then the total field MMF is the vector sum of these two components, FO and FAR. Okay. So this depends on the power factor of the load, which type of power factor we have. So again, we have three things. Okay, again I'm repeating, suppose my alternator is connected at full load. Okay, so total resultant field MMF, which is my FR, is the vector sum of this FO and vector sum of this FAR. Again, this FO and FAR is depend on the load, which type of load we have, either inductive or capacitive or resistive. According to that, my field resistance or base will be effect. So let me show you. So now we have three cases, as we have in a armature reaction. Okay, as we already have in a armature reaction. So first one is zero lagging power factor. Then zero leading power factor and unity power factor. So we have three cases. Sorry. So first of all, we are going for the zero lagging power factor. So you can see here, as long as the power factor is zero lagging, the armature reaction is completely demagnetizing. So hence my resultant FR is the algebraic sum of two components, FO and FAR. Okay. So field MMF method is not only required to produce rated terminal voltage, but it's also required to overcome the demagnetizing armature reaction effect. Okay. So you can say OA is my FO, AB is my FAR. So OA, so total OB is my resultant flux, FO plus FAR. So we require the higher MMF, field EMF. Okay, we require the higher field MMF. Why? To overcome this demagnetizing effect. To overcome this demagnetizing effect, we require more MMF. Okay, समझ में आ रहा है? सिंपली क्या हो गया? लेगिंग लोड है तो क्या है? इंडक्टिव लोड है, इंडक्टिव लोड है तो इफेक्ट क्या हो गई? डीमैग्नेटाइजिंग इफेक्ट हो गई। तो रेटेड वोल्टेज जनरेट करने के लिए हमें क्या चाहिए? ज्यादा एमएमएफ चाहिए। क्यों? क्योंकि एक एमएमएफ मुझे चाहिए वोल्टेज जनरेट करने के लिए और दूसरा एमएमएफ मुझे चाहिए जो ये डीमैग्नेटाइजिंग इफेक्ट है उसको नॉर्मलाइज करने के लिए और इसको ओवरकम करने के लिए। ओके, so I required more MMF. So you can see here the total field MMF is greater than the FO. So that is my first case, zero lagging power factor. Now second case, zero leading power factor. So you are aware about that zero leading power factor now. My total flux is increased, already increased. Okay, because my armature reaction flux is in the same direction of my main flux. So overall flux will be increased. So here effect is magnetizing. So you can see here, when my power factor is zero leading, then the armature reaction is totally magnetizing and it helps the main flux. Okay, to induce the rated terminal voltage. Hence my net field required is less than required to induce rated normal voltage. Okay, so you can see OA is again FO. Now it is in opposite direction, FAR. So my OB is equal to FO minus FAR. So my resultant flux, I required very much less amount of resultant flux to generate the open circuit voltage. So total MMF is required less than FO. Okay. Third case, unity power factor. So in unity power factor, you are aware about that. Armature reaction is cross magnetizing. Okay, if you are aware about the armature reaction, then this method is very much easy, ampere turn method. So under unity power factor, armature reaction is cross magnetizing. And what is its effect? It distorts my main flux. Okay, suppose my main flux is sinusoidal, then it will be distorted like that. Okay. So the FO and FAR at the right angles. So this is my FO, this is my FAR. So I have to take vector sum instead of algebraic sum. In lagging and leading, I have to do the algebraic sum, but here I have to do the vector sum. Okay. So this is the effect of load, or you can say power factor on the MMF method. So we have to actually draw this vector diagram or phasor diagram. Okay. So you can see here below is the following consideration for the MMF method. These are the considerations. First consideration, general case. What is the general case? Generally, we are assuming that my power factor is cos phi. Okay. And in such a case, the resultant MMF is to be determined by the vector addition of FO and FAR. Generally, always to find the resultant flux, what we are doing the vector sum. Instead of algebraic sum, we have to do the vector sum. Second, suppose my cos phi is lagging power factor. So when my power factor is lagging, the phase current IA, PH, it is lags my phase voltage by angle phi. Okay, you are aware about that. Power factor lagging kab hoga? When my power factor is lagging? Which type of load I have, then my power factor is lagging? capacitive. Inductive. For inductive load, my power factor is lagging. And when I have inductive load, you are aware about that. In inductive load, my current is always lagging by voltage. Okay. In inductive load, my current is always lagging my voltage at some angle. Suppose my load is purely inductive, then my current is always 90 degree behind my voltage. But here my load is not purely inductive, so my current is lag my voltage by some angle, and that is known as phi. You can see here, this is my voltage and this is my current. It is not purely 90 degree, but it is having some angle which is known as the phi. Okay, when it is purely inductive, then it is 90 degree lagging. Okay, but here we do not have that case. So this is my VTH and this is my armature current, phase current. It's having lagging by phi degree. And you are multiplying this cos phi with a cos, then you have a power factor cos phi. Okay. So now you can say the component FO is at the right angles to the VPH, while FAR is in the same phase with the current IPH. FO. So my component FO is at the right angle of my VPH, and my FAR, it is the same direction of my IAPH. Why? Because in short circuit, which current is flowing to the winding? Armature current. So in short circuit, which voltage is generated? FAR. Okay, in short circuit, we have MMF which is known as FAR. In open circuit, we have the MMF which is known as the FO. So FO is at the 90 degree, FAR is at the same direction in the IAPH. Now we require the FR. What is FR? Vector sum of FAR and vector sum of FO. Okay, vector sum of FAR and vector sum of FO. So what we have to do, we are taking the vector sum. It is in the same direction. So here we are taking this, doing this direction. Multiplying with cos phi, so FAR cos phi, and then I have to do the vector sum of FO and FAR. So that becomes my FR resultant MMF. That becomes my resultant MMF. So why this is so? This is because the armature current decides the armature reaction. Okay, armature reaction kab hoga? When armature reaction is created, when current is passing through the armature conductor, then and then armature reaction is created. In open circuit test, armature reaction is zero. In open circuit test, armature reaction is zero. Why? Because in open circuit test, no current flowing through the armature conductor, so there is no armature reaction. But in short circuit test, the current is flowing through the armature conductor, so that's why there is an armature reaction. Okay. So hence you can say, while finding the resultant field MMF, 1 minute. Okay, so hence while finding the resultant field MMF, what we have to do? FAR should be added to FO. So this is because the resultant field MMF tries to counterbalance the armature reaction to produce the rated terminal voltage. So phasor diagram of ampere term method or MMF method, you can see here it is. Now my FAR having two components, one is the FAR sin phi, another one is FAR cos phi. So we have to consider this cos phi, and then we are taking the resultant. So you can see here OAFO, ABFR and OBFR. Now consider triangle this OCB. So out of OCB, FAR is split into two parts. One is AC. My AC is FAR sin phi, and another one is BC. BC is my FR cos phi. So we have to do the vector sum. So FR is equal to FO plus FR sin phi whole square plus FR cos phi whole square. So this is the vector sum. Now suppose you have a FR. But what actually we have to find? We have to find this EPH and VPH. So VPH we directly have, phase voltage. But we have to find this EPH. So now, how we can find the EPH? Again, you can say from this phasor diagram. Now you have a FR, you have the FR, you have the FO, all the things you have. Okay, you have FR, you have FO, and you have FR. So now you can say when the load power factor is cos phi leading. Okay, here this is the vector diagram for. This is the vector diagram for lagging power factor. Remember this thing, cos phi lagging power factor. So this is the diagram for lagging power factor. This is the diagram for leading power factor. Suppose your load is capacitive. So we are taking voltage as a reference. So in capacitive load, now my current is leading the voltage. So now you can see my current is leading to the voltage at some angle, and that angle is known as the phi. Okay, and again your FR is in the same type of your I case. FO is always in the vertical mode. So you can see here the component FO is at the right angles to the VPH, and FR is in the phase with the IA phase. Now again I have to do the vector sum to find the FR. To find the FR. Now my FR is in this direction. This is my FO. So I have to take the sum. So it is in the opposite direction. So now this is my resultant flux. Okay, you already learned. See, when we have a leading power factor, we require the lower resultant flux compared to FO. So my FR is lower than FO. In lagging power factor, my FR is higher than my FO. It is already written. You can see here. In lagging power factor, my FR is always higher than my FO. FR higher than FO. In leading power factors, my FR is always lower than FO. So this is my FR, which is my lower than FO. Okay, it is the effect of load. It is the effect of load. Okay, so again, this is the vector diagram for the leading power factor. And now finally we have to find the voltage regulation. So using the relation 1 and 2, that is my relation 1 and that is my relation 2, we can find the FR for any power factor or for any load condition by using the MMF method characteristic. Okay. And once you are aware about the FR, you can easily find the induced EMF EPH. You can easily find the induced EMF EPH, which is required to rated terminal voltage VPH. Okay, so you have the EPH, you have the VPH from this FR. Okay, you can see here for FO, you are going to the open circuit test, so you have VPH. By finding the FR, again going to the open circuit characteristic, that is your EPH. So from this graph, you have the value of FO, you have the value of FR. You extend the graph, you have VPH, you extend the graph, you have EPH. So now EPH minus VPH divided by VPH into 100, that's your voltage regulation. So this is the MMF method, or you can say this is the ampere turn method to find the voltage regulation. There are some key points. These ampere turn methods of the voltage regulation always give you the voltage regulation lower than the actual. Suppose my actual voltage regulation, you can say it is 2%, 5%, but it is always give you lower than actual voltage regulation 5%. Then by using this method, you are getting 4%. In synchronous impedance method, it will give you the higher. Suppose your actual is 5, they are giving you 7%. Okay, then we are moving for the third method, which is known as the ZPF method, zero power factor method. Okay, that we will learn in the next lecture. So this is all about the MMF method to find the voltage regulation. Okay, it is simply nothing but if you are aware about the armature reaction, then these 3 slides are for the armature reaction only. And from that we are drawing the phasor diagram. Okay. And this is the open circuit test and the short circuit test characteristic. That's all from my side. If you have any doubt, you can ask me a question. Those who are attending the session online, please write down your enrollment number in a chat for the attendance. And if you already written your number, if you want to leave, you can leave the session. Thank you. Okay, so thank you everyone for attending the session. Now I may end this meeting for everyone else. Thank you.